Chapter 9, Topic 9.1, Controlling Microorganisms. I should warn you, I think this is the most important chapter in the entire textbook. You can use information in this chapter to prevent nosocomial infections, including protecting yourself. It can also help you prevent illnesses and food spoilage at home. The benefits just go on and on. So, the objectives for this particular topic are clearly define the terms sterilization, disinfection, decontamination, sanitization, asepsis, and degermination. Identify microorganisms that are most resistant and least resistant to control measures. Define static and cidal, and name 4 categories of cellular targets for physical and chemical agents. In this topic, we will be covering terms involving the controlling of microbes, an overview of methods used to control microbial growth, the relative resistance of various microbes to control methods, means of microbial control, the rate of microbial death and what affects that, and the modes of action of various methods. For this course, you will need to learn and be able to apply and use the terms in this table. These definitions cover the meaning that is common usage in the healthcare industry. But I feel it's important to know the legal definitions for these terms. When the EPA and the FDA are clearing products for use as sterilants and disinfectants, they have certain standards that the products have to meet. For example, a control method that is cleared for sterilization has to show removal or kill of 10 to the 6th thermal-resistant endospores. In other words, the manufacturers can't prove that their product will destroy or remove every living organism. They can prove that their product will remove or kill 1 million endospores. And those endospores come from bacteria that live in hot springs. That's the thermal-resistant part. So they eat malfunctioning sterilizers for lunch. So what the manufacturer will put on the bottle and in the directions will fit the legal definition as opposed to the definition of the users of the product. So I've gone over the legal definition for sterilization. Disinfection is the reduction of vegetative bacteria by 3 log 10. What does that mean? If you start out with 1 million salmonella on a fork, that fork is considered disinfected if you end up with 1,000 salmonella on the fork. That also relates to a 99.9 decrease in what you see on a lot of bottles. So, are the manufacturers lying to you? No, but you need to understand the standards they are required to meet. Disinfection, in real-life practice, is not sterilization or even complete removal of vegetative bacteria. The plan with disinfection is to reduce the numbers of microorganisms to the point that they are below their infectious dose, or so that the average immune system could take out the salmonella on the fork that you are using and you won't get sick. Realize, though, that most people in the healthcare situation are sick with something already, and their immune systems are busy on the other side of the body, so to speak, and their infectious dose may be less. Let's move on to decontamination and sanitization. The legal definition for a sanitizer or decontamination process is to reduce vegetative bacteria by less than 3 log 10. In other words, they didn't make the cut to be a disinfectant, but they still reduce numbers of vegetative bacteria. The legal definition for antiseptic or antisepsis is the same for disinfectants, just with something that is safe for use on living organisms. We usually mean animals and humans in that. The legal definition for degerming is the physical removal of microbes, including endospores. You can have a disinfectant degerming, antiseptic degerming, and sterilization degerming, and so on. But keep in mind that degerming doesn't require that the microbe be killed or inactivated. The wastewater used in degerming should be disinfected or sterilized. Do I have you scared? Don't be. I just want you to understand where the manufacturers are coming from so you can use their products in an informed and intelligent fashion. We will be doing problems in class to give you practice in using, nay, applying these terms in practical situations. Here is an overview of microbial control methods. You should be able to redraw this figure by the end of this chapter. This figure is straight out of your book, and from my years of testing sterilizers and disinfectants, I disagree with it. Well, the middle anyway. Prions are next to impossible to inactivate. Pretty much, you are limited to incineration or treatment with specialized enzymes developed specifically for inactivating prions. Endospores are, of living things, the next hardest to kill. They are resistant to heat, drying, osmotic pressure, radiation, and nearly all chemical control methods. We use thermal-resistant endospores to make sure sterilizers are working, because they are the baddest of the bad. Enveloped viruses are easy to inactivate. You break up their envelope, they lose their receptors, they can't attach to their host cell, thereby not infecting it. Well, what I disagree with the figure is the middle. Non-enveloped viruses, at least the ones I worked with, are right up with Mycobacterium in difficulty to inactivate. Protozoan cysts are right up there too. So, let's go with my figure, which isn't as pretty, but I'm going to test you on it. I have 4 categories: impossibly resistant, most resistant, medium resistant, and least resistant. You will see variation within the categories, but these categories work for practical applications. Prions are the sole occupants of the impossibly resistant microbial forms. At least I hope we don't find anything else that is as bad as prions. For resistant forms, I would put anything that is in a resting or protected form of the microbe. For resting forms, that's endospores and protozoan cysts. They're resting. They're not actively metabolizing. Mycobacterium, or the genus of acid-fast bacteria with pathogens, are protected by their waxy cell walls. Non-enveloped viruses are protected because they are built to take very unfavorable conditions. Medium-resistant forms are vegetative bacteria, vegetative protozoa, fungi, and fungal spores. I would include Staphylococcus and Pseudomonas in this category, but up at the top of the category. When you are trying to kill stuff on a countertop, the chemical disinfectants, at their proper dilution, will reduce their numbers by 3 log 10, the same as fungi, which are at the bottom of the category. Do keep in mind that Pseudomonas will eat just about anything, so if you will find them happily growing in diluted chemical disinfectants and even sterilants, so they deserve respect. That is why, if the directions say to dilute immediately before use, you better follow the directions. I've already gone over why I agree with the textbook about enveloped viruses, but we often treat them like the most resistant forms. Why? HIV is an enveloped virus. It is relatively easy to inactivate. That's why it's transmitted by fluid-to-fluid contact rather than fecal-oral transmission. They wouldn't survive drying in the environment, nor would they survive stomach acid. But when they are protected by blood and other fluids, do you want to risk getting a non-curable, lethal disease? Do you want to risk being infected with 1,000 HIV virions after using a disinfectant to clean up a blood spill? I wouldn't. I always treat blood like it has endospores in it. It is the safer bet. I've scared you again. Well, a little bit of fear is healthy. Let's move on to means of microbial control. What we've talked about to this point are agents, disinfectants and such. The book to this point has stressed the process, disinfection versus the agent or the disinfectant. We also classify agents by how they do what they do. If a disinfectant kills or inactivates the microbe, they are called cidal. So a chemical that kills bacteria would be bactericidal or a bactericide. Let's go over practical matters in considering the microbial control method that should be used in any given situation. First, what does the application require? Is the instrument going to be contacting the patient's bloodstream? I'm thinking scalpels and needles. It had better be sterile. Is the instrument going to be contacting intact mucosa? Think tongue depressors. Trust me, the wooden tongue depressors aren't sterile, but they don't have high numbers of microbes because they are dry. They probably have endospores on them in low numbers, but you swallow a few endospores every time you swallow. Second, is the item going to be reused? Most clinics don't change out countertops after each patient, so you better get them as close to sterile as you can. That's why we put paper on examination tables, so we can throw them into the garbage rather than trying to figure out how to perform high-level disinfection on the vinyl. Third, is the resistance of the item. I can use moist heat to sterilize stainless steel, but what if my plasticware will melt? Better not use moist heat. What if I'm using carbide steel instruments? They are popular in the dental industry because they hold an edge better than stainless, but they rust when exposed to moist heat. Fourth, is the control method appropriate? UV radiation is effective on endospores if you expose them to the UV long enough, but a sheet of paper will block the UV radiation. So is UV a good idea for use in disinfecting or sterilizing toothbrushes? Believe me, you can't get the UV into the center, where all the toothpaste crud and oral bacteria are partying, so don't bother buying the UV toothbrush products. Also keep in mind that UV breaks down plastic, so don't use it on plastic items. This goes along with number 5. Will the agent penetrate to the necessary extent? I will mention that we are talking about bioburden in the next slide, which affects penetration. Sixth, don't bankrupt yourself buying the best if the second best will work just as well for the job. But don't buy the second best if it doesn't do the job. You don't want to risk an illness or a lawsuit. And most hospitals and clinics can't afford to pay someone to just do microbial control. Well, hospitals control infection control specialists and employees dedicated to sterilization, but that's a big company, so to speak. And lastly, is the method safe? Don't use a volatile chemical in a closed room. Don't use bleach on something that will contact a patient's blood or food prep surfaces unless you get all that residue off. When we're discussing the control of microbial growth, we need to know how many microbes are being controlled or killed by our control methods. So for that, we need to know the number of microbes. To do that, we use the same methods that we talked about in Chapter 6. This would be direct microscopic count, plate counts, that sort of thing. Once we've determined the number of microbes, then we can determine how well a control method works by determining how many microbes it has killed. Environmental influences also play a role in the rate of microbial death. For the sake of example, I'll use the example of a chemical disinfectant such as Lysol. Now, environmental influences are important to other control methods such as refrigeration, steam sterilization, etc. But like I said, I'm going to go with Lysol as an example. So one of the environmental influences is bioburden. Now, bioburden is a technical term that refers to anything of biological origin that influences the activity of our Lysol spray. So we're talking about blood, vomit, saliva, etc. Biofilms also influence the rate of microbial death, influences how well Lysol can kill. When you have a biofilm, the gunk, the slime that is produced by the microbes to hold themselves together, keep out chemical disinfectants and also makes physical disinfectants have to work harder to kill microbes. So biofilms affect the rate of microbial death by slowing down the rate of death. Temperature also has an effect on microbial death. With Lysol spray, it has an optimal temperature in which it works, kind of like optimal growth rate in microbes, but in this case, with chemical disinfectants, temperature plays a role in how well they act. Some are set up to work at higher temperatures, some work better at room temperatures, some work better at lower temperatures. Temperature also has an effect on how susceptible the organisms are to kill, because generally speaking, if they're already stressed out by being above their optimum temperature, then their death rate is accelerated by physical methods. pH also plays a role in microbial death rate. Once again, Lysol works best at a certain pH. If things are too acidic, if things are too basic, that's going to throw off how well it works. For this next one, suspending medium, Lysol spray isn't a really good example because you don't mix it with anything. But there's many disinfectants that you do take and you mix it with something else to bring it up to in-use concentration. Now, with some of them, if you mix them with water, they're not going to dissolve real well and they're not going to work very well, and they need to be mixed with a hydrophobic suspending medium. Most disinfectants, though, do well in a aqueous or water suspension, but once this ties into bioburden, if you're using tap water to mix up something, sometimes that will inhibit the action of the disinfectant, even though it's not a bioburden. It's an inorganic burden, still causes problems. Exposure time. Disinfectants, when they're tested, the standard is generally to test them at 10 minutes. I don't know why this is the standard, because nobody leaves a disinfectant sitting on a counter for 10 minutes. With sterilization methods, that makes more sense. You can pop something in a sterilizer for 10 minutes, see what the microbial death rate is. But with exposure time, generally speaking, we take a look to see what the rate of microbial death is for a set exposure time. And it's usually either 1 minute or 10 minutes. Some sterilization or control methods take a shorter amount of time, and so you don't have to use them for as long a time. Others take time to be able to penetrate the bioburden, the biofilms, the suspending medium, etc. The last thing that affects the rate of microbial death is the microbe itself. Some microbes are just tougher than others. Therefore, they're harder to kill, and we have to use more stringent measures, longer exposure time, all of that fun stuff. So all of these things go into determining rate of microbial growth, and they also are part of how we determine how well or how effective a control method is. Now at this point, if I may be allowed a little bit of reminiscence, I spent several years doing disinfectant testing and sterilizer testing, and we took all of these things into account, usually with temperature, pH, suspending medium. We would go with what the manufacturer recommendations were. But to add in bioburden, blood is the most convenient one, and it's the most common one out in a clinical environment. So when I was doing the testing, guess whose blood we used? Yep, you got it. We used my blood, and we also used the toughest microbes that we could. From previous years of testing, we found that if something would kill the toughest microbes, then why bother with the wimpy ones? We knew that a disinfectant or a sterilization method would kill the tougher ones, it'd kill everything else. Before we leave the topic of rate of microbial death, let's talk about how rate or score microbial death. We generally do this on a logarithmic scale. Now in this chart we have an arithmetic scale where for the time frame here we're looking at our exposure time as being 1 minute. In this case, in 1 minute we get 90% kill of our organisms. So with the arithmetic scale, we can see looks like there's a whole lot here. This is still 90%. Still 90%, looks like we've reached 0. So we generally represent this as a straight logarithmic line. Okay, so once we've killed 90% of the population, that is a 1 log decrease. Now, definition time. Federal standards are, for sterilization, you're going to be killing all the microbes. So we're generally not talking about log decreases. We're generally talking about log decreases when we're talking about a disinfectant. A disinfectant is anything that will decrease the microbial count by 3 logs, or 99.9% of the microbes in the acceptable exposure time. If it's below that, and also if it's intended to be used on surfaces that people are going to be eating off of or putting in their mouths, we call this sanitization. Sanitizer is something that will kill less than 3 logs in the acceptable exposure time. So let's take a look at what happens when we have different starting numbers. In this chart, we have it all in logarithmic representation. Here we have a high microbial load. So even though we're seeing the same kill rate As for a low population load, you can see that we reached 0 in a short amount of time than we do for the high population load. It makes sense. If you start out with 1,000,000 organisms and you go to 10,000, that's a 1 log reduction. If you start out with 1,000 organisms and you have 1 log reduction, that goes to 100. So you reach your end point much faster. This is also why we have federal regulations about how many starting microbes you can have. For example, the FDA goes and inspects meat and slaughterhouses. If you have a carcass that has been all cleaned out, the feces and intestinal contents have been gotten rid of, the meat lasts longer. You have a low population load, and you don't have to do as many microbial control methods to keep it consumable for humans. For example, if you have a low population load on a steak, then you don't have to cook it for as long to kill all of those little nasties. Here's another one. If you have a dirty dish that has a high microbial load, then you have to treat it for longer, either by washing it or putting it through a commercial dishwasher to lower the microbial load to the point where it's non-hazardous for the bulk of the population. If you already have a clean dish, then you don't have to go to extreme measures. By the way, both of these are examples of removing bioburden. Lastly, I do want you to know the modes of action. If you know how something works, you can figure out if it will work on a most resistant microbe, or if you're better just using it on the medium to easy stuff. There will be exam questions applying to this information. So, here are reminders of what the learning objectives are for this topic. Be able to clearly define the terms sterilization, disinfection, decontamination, sanitization, asepsis, and degermination. Identify the microbes that are most resistant and least resistant to control measures. Define static and cidal. Name 4 categories of cellular targets for physical and chemical agents.